So this is the solution to the chemical equilibrium question from 2020 higher level chemistry. Question 9. When 3.0 moles of carbon monoxide and 1.0 moles of steam were mixed together in a container of fixed volume V and in the presence of a suitable catalyst, the following chemical equilibrium was established at a temperature of 800 Kelvin. Okay, so the first thing you're asked to do is to explain chemical equilibrium. Why is the chemical equilibrium described as dynamic? And to state Le Chatelier's principle. So these are your definitions. Chemical equilibrium is a state of dynamic balance in a reversible reaction where the rate of the forward reaction is the same as the rate of the reverse reaction. Dynamic means that the forward and reverse reactions continue to produce products and reactants, i.e. the reactions don't stop. And Le Chatelier's principle states that if a stress is applied to a system at equilibrium, the system readjusts to relieve the stress applied. In part B, you were asked to write the equilibrium constant Kc expression for the reaction above. So when you write a Kc expression, always write out the equation to which it pertains to. So here we have a reversible reaction, and the Kc expression is written as the concentration of the products divided by the concentration of the reactants. So products on top, reactions on the bottom. We always use square brackets to denote concentrations, and we never put a plus sign or a negative sign. We're not adding or subtracting, it's multiplying the products on the top and the reactants on the bottom. Okay, so for this particular one here, we'd have the Kc is going to be the square root of concentration of CO2 times the concentration of H2 divided by the concentration of CO times the concentration of H2O. So products over reactants. Also note in this particular example, we only have 1 mole of each of the products and reactants, okay? So therefore, the powers are all 1 on all of these concentrations. In part C of this question, we're told that the equilibrium constant for this reaction is at 800 Kelvin is 4.0. We're asked then to calculate the number of moles of carbon monoxide in the equilibrium mixture at this temperature. So in this particular question, we know the value for the Kc, but we want to work out the number of moles of carbon monoxide at equilibrium. So in order to do this, we set up a table. We have our reactants and we have our products, okay? So we have carbon monoxide and water being our reactants, and CO2 and H2, hydrogen, being our products. Okay, so remember ice. So we want to write down initially how much of each we have. So at the very start of the question, we were told when 3.0 moles of carbon monoxide and 1.0 moles of steam, which is water, were mixed together in a container of fixed volume V, okay, and in the presence of a suitable catalyst, the following chemical equilibrium was established. Okay, so therefore that means that initially we have 3.0 moles of carbon monoxide, 1.0 mole of water, and no CO2 or no hydrogen, no products, okay? Now, we do not know exactly how much reactions were lost or products were made, so we use the value X, okay? So we are saying that we made X amount of CO2 and we made X amount of hydrogen in this reaction, and because the reaction ratios are all 1:1, that means that we lost X moles of CO, carbon monoxide, and we also lost X moles of water. So that's the change in the numbers of the amounts or moles of our reactants and products. So therefore, at equilibrium, we have ended up with 3.0 minus X moles of carbon monoxide, 1.0 minus X moles of water, and we have X moles of CO2 and X moles of hydrogen, H2. Now, we would like to know their concentrations at equilibrium because that's what we need to sub into our formula up here, our Kc value, okay, or our Kc expression. So, so the concentration at equilibrium is always going to be the number of moles divided by volume. Remember, using the not very complicated triangle, concentration is equal to number of moles divided by volume. So the volume in this question is just given as V, okay? So therefore the equilibrium concentration of carbon monoxide is 3.0 minus X over V. For water it's 1.0 minus X over V. And for CO2 and hydrogen they're both X over V each. Now let's go back to our equilibrium constant, okay, our equilibrium expression, Kc. Alright, so we'll write that out again down here. And now we sub in the values that we had from our table. Okay, so for our concentration of our products, we have X over V by X over V. And for carbon monoxide and water, our reactants, we have these values, okay? So taken from the table. And we let that equal to 4.0, okay? So what we're going to do now is we're going to solve for X, okay? Now luckily for us, because we have volume on the top and the bottom, and it's a constant, we can actually just cancel that all over there, okay? So now let's cross multiply. Let's do some algebra, okay? Let's cross multiply. So we're going to have x squared, x by x, okay, divided by 3.0 minus x by 1.0 minus x. And now we can cross multiply. So we're letting that equal to 4.0. So 4.0 times the bottom line here, okay, will give us this expression, okay, is equal to x squared. Now, the next thing I'm doing now is I'm just multiplying out my brackets. So I'm using just using my arrows here to make sure I don't forget anything, okay? So I'll multiply by 4 later on. So just leave that outside the bracket for now. So 3 by 1 gives me 3. 3 by minus x gives me minus 3x. Minus x by 1 gives me minus x. And minus x by minus x gives me x squared, okay? So now I can multiply that by 4, okay, when I tidy up the bracket, okay? And then I have 12 minus 16x minus 4x squared is equal to x squared. So I'm going to bring my x squared over, okay, everything to one side, okay, and tidy it up, okay, simplify to 3x squared minus 16x plus 12 equals 0. So I have a quadratic here, folks, okay, and I want to solve this to find the value for x. So I use my good old minus b formula, okay, so I'm solving this equation. I'm using the minus b formula, okay, straight from my table book, okay. I've written out my minus b formula. I've established my a is 3, my b is minus 16, and my c is 12, okay. And I sub them into the formula, okay, and I do some number crunching, okay, using my calculator. Okay, so I'll end up with two values for x, 0.9028 or 4.4305. So let's look at those two values. One of those makes sense and one of them does not, okay? So when I go back to my table for my equilibrium calculation, okay, I see that I started off with 3 moles of carbon monoxide and I'm losing x moles. So there's no way I could be losing 4.4305 moles if I didn't have those to start with. So this is the answer we delete, and we take the 0.9028 answer, okay? So therefore, at equilibrium, the number of moles of carbon monoxide that I have, okay, is going to be 3.0 minus the x, which I just figured out, okay, which will give me, at equilibrium, a value of 2.1 moles of carbon monoxide at equilibrium. In part D of this question, I'm asked to predict the effect, if any, of adding more steam at 800 Kelvin to the equilibrium mixture. First of all, on the value of Kc, and then on the equilibrium yield of hydrogen. We need to justify our predictions in each case. Okay, so we're adding more steam. So let's look at our reaction, equilibrium reaction. Okay, if I add in more steam, okay, basically that's applying a stress to this system at equilibrium, okay? And basically what's going to happen is this equilibrium system is going to adjust to try and bring back down that amount of steam water, okay? So it's going to try and use it up, okay? Now, so what effect will that have on the Kc value? Well, remember, okay, the only thing that can affect the Kc value is a temperature change. So therefore, changing a concentration or changing a pressure of the system is not going to have any effect on the Kc value. So the effect on the Kc value is none. Only temperature changes the effect, temperature changes can affect the Kc value. So that's my justification. Part 2, okay, will adding more steam affect the equilibrium yield of hydrogen? Well, yes, that there will be an effect there. If we add in more water, okay, according to Le Chatelier's principle, okay, more hydrogen will be produced, okay, so we're going to increase the yield of H2 because the forward reaction is going to be favoured according to Le Chatelier's principle, because it's going to try and use up this excess water, this excess steam, so therefore it'll shift, the equilibrium will shift temporarily to the right, it'll favour the forward reaction, which will increase the yield of hydrogen. Okay, part E. State and explain the effect on the value of the Kc of increasing the equilibrium temperature. Okay, so let's go back to our equilibrium reaction again. So we notice that the delta H for this reaction is a negative value, which means that the forward reaction is exothermic, and therefore the reverse reaction, the back reaction, is endothermic. Okay, so if we were to tamper with the reaction at equilibrium and increase the temperature, that's a stress. Okay, so according to Le Chatelier's principle, the system will readjust to minimize or oppose that stress. So if we increase the temperature, the system will want to bring the temperature back down. So therefore it favours the endothermic reaction. Okay, and in this case, that means it's going to favour the reverse reaction, because this is the endothermic reaction in this particular question. Therefore, the product concentration will decrease and the reactant concentration will increase. Okay, so if I favour the back reaction, okay, that means that I'm going to be doing more of the back reaction. So my products are going to decrease because they're being used up more, and my reactants are going to increase because they're being made more. And if I look at my Kc value, that means that my product concentrations are decreasing, my reactant concentrations are increasing. So overall, that's going to lead to a smaller value in Kc, a decrease in the Kc value.